Today, we want to start looking at double integrals. We've talked about the concept behind how an integral is going to work. We're going to upgrade our idea of the integral over some interval of f of x dx as the area under the function, but above the interval. We're going to upgrade that to a function of two variables. So where the function f of x is a one-dimensional curve in R2, a function f of xy is a two-dimensional surface in R3. So we wouldn't want to talk about the area under the surface. We would want to talk about the volume under the surface. So recall that f of x, we think of a function of one variable as a one-dimensional curve in R2. And we know what happens when we upgrade our function of x to a function of x and y, we end up with a two-dimensional surface in R3. So we're not going to be looking at a function of two variables above an interval. We're going to start by looking at a function of two variables above a region, an area. So notice that the interval from A to B, that's an interval, it's one-dimensional. All right. So where a function of a single variable once again, we've got our function up here, and we're finding the area under the curve and above the interval. So under the curve and above the interval. Those are our boundaries on this little area. So when we upgrade our function of x to a function of x and y, instead of dx being a small piece of the interval that came out of a delta x, dx is a small bit of the interval, because our assumption is going to be, we want to use multiplication. I want to do height times width, but the height is all variable. So we assume that the height is constant for some small change in that interval. Because if the function is continuous, it will change very little over a very little change, a little bit of the interval. So when we integrate a function of two variables, we're not going to find the area under a curve and above an interval. We're going to find a volume below a region, volume under a surface and above a region. So here's what it's going to look like. We're going to integrate f of xy, but instead of dx, a little portion of an interval, I'm going to say dA, a small piece of area, and we're integrating over a region. So this is going to be the volume under the surface and above a region R. So we're calculating volume here by taking the cross-sectional area and multiplying by the height. Volume is length times width times height. Length times width is area. So the volume is height times area. So our f of xy is still going to be the height. And our region R is going to be an area rather than just a width. Our function f of xy, we know, is a two-dimensional surface in R3. And the dA is going to be a small bit of this area, the region. Upgrading area, we're upgrading our height is still one-dimensional because we're plugging in an x and y and coming up with just the height, but it becomes a volume because dA is now an area, not a length. Also, I got to change our notation over here. We're describing a region. So what we're looking at in an integration standpoint is we're going to take a dA, which is going to be a small piece of a region. So we've got a region down here in region R. See, the difference and why things are more complicated now is that intervals are really easy to describe. We start at A, we end at B, that's an interval. That's the only thing that we integrate over in with a function of one variable. But when we're plugging in two variables, we got to gather up a bunch of coordinates x and y. And now we don't just have a length, we've got some area, and that area can have lots of different shapes. That's the problem when we upgrade our interval to a region. It's still just an area, but it can have many different shapes. Intervals have one shape, length. Areas can have all kinds of different shapes. That's what's complicating things. Areas can have funky shapes. Or I should say regions. Regions can have funky shapes. Intervals are always boring shape. Regions can have funky shapes, intervals can have boring shapes, or intervals always have boring shapes. Those aren't official terms, so don't be searching your math book for funky shapes. But the thing that we're doing is the same. We're finding a little piece of area choosing a point and evaluating the function at that point. And calculating the volume of this little box. The height is given by the function. We're assuming that the function is constant for some small piece of the region, dA. And then we get to use multiplication, height times area, to get the volume. Saying volume is height times area. So the way that it works, our assumptions are working the same way. I want to use multiplication, but one of my factors is variable. So I assume that factor is constant for a small change in the other factor. We've just gone from length times width to height times area. All right. So the challenge for us is going to be to describe the region in a way that the integral can understand. So what we have to learn, the skill that we have to have, is to describe the region in a way that the integral will understand. That's the skill that we need to build now. Describe the region so that the integral will understand. We've got to figure out how to communicate with this tool that we have, the integral. So let's talk about how we are going to describe regions. Our big hope, this is what we want, is that we can describe a double integral with an iterated integral. We want to describe the integral with an iterated integral. What we mean is that this is what we want. We want to be able to describe the integral over some region of a function of x and y dA. Iterated just means we're going to perform multiple integrals, just little pieces at a time. We just want a piece at a time. So we want to describe the integral as, say, the integral from y1 to y2, and then the integral x1 to x2 of f of xy dx dy. And so what we're looking at is a two-step integral, where we first integrate with respect to x, and then we integrate with respect to y. X1, X2, Y1, and Y2 is what we're going to use to describe the region. The endpoints of these two integrals are going to describe the region. So we're using X1, X2. So it's in the integration, in the integral setup, that's where we describe the region. So let's look at an example. Let's use a double integral to describe a region. So first, I'm going to start with this region. Let's see. So we're going to be looking from the top down. Remember that our skill is to be able to describe the region so that we can just drop it into the integral. So we're going to focus our view on a top-down view. Above this, we're going to be looking at the XY plane from the top. And so above this, somewhere, it's even above the camera. I made it high enough so that it wouldn't like get in the way of the camera. The first example I picked, the surface was like right here, and then you couldn't see anything because I was using an opaque surface. I tried a transparent surface. It was just like putting a color filter on my camera. So I moved the surface. I put +5 at the end of it. And so now it's above the camera and you don't have to worry about it. So clever move there, just adding 5. We're focused on describing the region in the XY plane, and the function is going to be sitting above this. So let's say we have a square or a rectangle that goes from 1 to 5 on the X, and then from 2 to 4 on the Y. So let's suppose that we have a function sitting above this rectangle in the XY plane. So this is the region R. The way that we're going to describe it is we're going to say what X falls between, and then we're going to describe what Y falls between. So I'm going to set up a double integral. And my dx integral, I just have to look at what values of X, what values X falls between. So I get to describe this region by my dx part will go from 1 to 5. Because those are the X values. That's the left and right of my X, the lowest and up and highest X values. And then my dy, or my Y values start off at 2 and go up to 4. So on my Y integral, I'm going to go from 2 to 4. So we just integrate the function of X and Y with respect to X, then evaluate from 1 to 5, take that result, integrate with respect to Y, then evaluate from 2 to 4. Same thing we do in all math problems. Just drop it back to a simpler problem. Break it down into steps if we can. Here's an important thing to remember that I forgot to mention yet again, but it's just in time. If you integrate the function 1, recall. So think back. If we integrate from a to b the function 1 dx, mechanically, the integral of 1 is x, and then we evaluate from a to b. It's equal to b minus a. When we integrate the function 1, we get the length of the integral. Sorry, length of the interval. So if we integrate the function 1 dA over some region, we'll get the area of the region. Because we're going to take the area of the, remember what this is built on, the area of the region multiplied by the height. If the height is always 1, we're just going to take the area of the region times 1, we'll get the area of the region. So if we integrate from 2 to 4 on y and 1 to 5 on x, the function 1, we should get the area of this region. Let's find out. So if we integrate, I'm going to remind ourselves that 2 to 4 is a y integral. And then I'm going to remind myself that 1 to 5 is an x interval. If we integrate the function 1, that should just give us the area of the region. Now, this means we have to learn how to integrate with respect to x and then with respect to y. Let's just guess at what we would do. So this is going to, I'm going to integrate the function 1 with respect to x. That's going to give me an x that I'll evaluate from 1 to 5. I still haven't integrated with respect to y. So I still have my dy integral out here. Now, when I evaluate x from 1 to 5, I still haven't done my y integral, so it's still from 2 to 4. Plug in 5, plug in 1, and subtract. And we can see that this is going to give us the area of the region, just like we planned, because now we'll integrate with respect to y. Now that I've plugged in values for the x, the integral of 4 is 4y, and I evaluate this from 2 to 4. And promptly run out of space. I thought I had dropped this down one line, but I didn't. So I do 4 times 4 minus 4 times 2, which is 16 minus 8, which is 8, which is the area of the region. Don't integrate, instead of thinking of it as integrating both, integrate them one after the other. So imagine integrating one after the other. So another thing to note, since we're looking at double integrals, so I set this up as a dx dy. There's no reason that we have to go in alphabetical order. So I could set this up as the integral as x goes from 1 to 5, and y goes from 2 to 4. The left and right, and then the up and down. But in this case, the dy integral should be listed first. And then the dx integral will come second. So we can change up the order. In this case, it wouldn't matter because we're just describing a rectangle. The region is a rectangle, very simple. Any questions? So earlier, we mentioned that when we have a region that's going to have an area, we're not always going to get rectangles. Intervals always have boring shape, but regions can have funky shapes. We're going to describe the regions using the same idea. What is X between? What is Y between? So those are always going to be our questions. What's X between? What's Y between? That's how we're going to describe the regions. We're describing the regions by thinking about what's X between and what's Y between, in whatever order is most convenient for us. So when we're integrating, I'm going to set up a dx dy. When we're setting up a double integral and describing a region, we're just saying what's X between and what's Y between. When we set up a double integral, the last integral, that is the one on the outside, that has to be constants. But our inside integral can be a function of upcoming variables. So X can go between, say, a function of Y and another function of Y. The inner integrals, the bounds on the inner intervals can be functions of upcoming variables. The last integral has to be constant. So if I set this up in the other direction, my last integral for in this dy dx integral, you know, back when we were coming up with words for all these things, I said all this inter stuff is going to be a problem. And then everybody else is like, oh, only for you, Leach. And it's pretty much true. I'm the only, I think I'm the only one. This double integral, the last interval describing the X has to be constant, just like it was constant for these Y's. But your inner interval can involve functions of upcoming variables. So here's a version dy dx. So your last integral has to involve constants. Your last integral must only use constants. Earlier integrals can use functions of upcoming variables. Notice I said earlier instead of first and seconds. because here we are looking at functions of 2 variables, but you know that in a couple of sections, we're going to be talking about functions of 3 variables, and we're just going to be stacking 3 integrals. When I say we can use functions of upcoming variables, I mean those are the variables that we haven't integrated yet. Let's take a look at some variations of this, because we're going to start with a rectangle, and then we're going to start messing with the rectangle. And we're just going to set up double integrals. Remember, what's x between, what's y between, in whatever order happens to be convenient for us. So let me start with a region that is just a rectangle. Nope. I didn't want everything to just start off at zeros last time, but this one is going to be just zeros. Over here, we're going to end at, let's say this is going to be over at 3, and 3 squared is 9. And here's our region. So we want to describe this region with a double integral. Remember, the function is sitting on top. The function doesn't matter. What matters is how we describe the integral, or sorry, describe the region so that the integral will understand. So I can just say, well, x goes from 0 to 3. And y goes from 0 to 9. So I can describe this with 2 iterated integrals. I can integrate the x first. So x goes from 0 to 3. And so my first integral is a dx. And then I can integrate y from 0 to 4. So here we have the region as a dx dy integral. We just have a rectangle, nice and boring, so I can change the order. Oh, 9, not 4. That's what I wrote, see? I don't know what you're talking about with 4. It's a 9. Oh, you didn't talk about 4, dang it. But we can integrate this in the other order. I'll just move the y's to the inner integral, or the first integral. And then we'll integrate dx second. What's x between? What's y between? X is between 0 and 3. Y is between 0 and 9. The last integral only involves constants, so we're okay. What we have to work on now is not having nice rectangles. So let's come up with a new region. And I'm just going to carve a new region out of this old region. with a parabola. Once again, we're not trying to find the area. The point is not to find the area. The point is to describe the region so that I can find a volume if this is the floor and I have some variable height above it. Now we can see on the outside, x goes from 0 to 3. This is still cut from this rectangle that we had before, where x goes from 0 to 3 and y goes from 0 to 9. We got to think about what's x between and what's y between. And we can describe this with two different integrals, two different double integrals. My last integral has to be constants. So I'm going to start with the easier one first. My x's go between 0 and 3. I'm going to say my x's go between 0 and 3. So I'm integrating dy dx in this case. Now I got to figure out what my y are between. So what we're going to do is pick a generic x and see what values of y we are between. So I pick a generic x, and y starts off at 0 and goes up to our function. So the bottom lowest y value is 0, and it goes up to the function 9 minus x squared. My last integral, the dx integral, is with constants. My first integral involves functions of the upcoming variables. Just like before, we can do the process, we can write the integral in the reverse order. So if we consider the outside integral, remember the last integral has to only involve constants. So I could say as a dx dy integral, y goes from 0 to 9. Last integral is constants. Then I have to pick a generic y value and see what is x between. X starts off at 0 and goes up to the function. So x starts off at 0 and ends at the function, but I can't use 9 minus x squared. X is the variable that we're integrating with respect to, not an upcoming variable. So I just have to turn my function around. Instead of writing 9 minus x squared, I'll have to write this as, let's see, the square roots of 9 minus x. Yeah. When we rewrite this, notice that the square root is going to have a plus or a minus, and I clearly want the plus side because my x's are all positive in this problem. So we integrate from the lowest x value is 0, and the highest x value is on the function as a function of y. So here's how we describe this region in a dx dy integral. Any questions? All right. If you're unsure about what we're doing in this process, and you're not comfortable with doing any problems because this is confusing, remember we've done like 3 examples and 2 of them were the easiest kind, rectangles. We've done 1 example that wasn't a rectangle. So if you're expecting to understand things really well at this point, you are incorrect. There's no way. Also, if you understand this example, you're like, oh yeah, totally got it. That just means you stepped out onto the basketball court, picked up a basketball for the first time and happened to be able to throw it through the hoop. And you probably don't understand. You just got lucky on this first example. But think about the procedure. Don't look at the form and try to match the form. Think about the procedure and what we're trying to express with this set of symbols. What are we trying to do? We're integrating a function. The double integral is how we describe the region. Here I'm going to say, what does y go between? Y starts off at 0 and ends at 9 minus x squared. What does x go between? X starts off at 0 and ends at 3. From an building an integral standpoint, start with the outer one first. Say that one has to be constants. X is between 0 and 3 in a dy dx, or the outer one has to be constant. So in a dx dy, the y's are between 0 and 9. You don't care about the shape. You just care about the lowest and highest y values or the lowest and highest x values. Any questions? Tomorrow, we're just going to practice describing some more regions with double integrals. And we'll talk about why it's going to be important to be able to describe them in both directions. You can't just pick one and say, I'm always going to do dx dy, because then you'll come across an integral that is best described the other direction. For context, remember that we can use, for context, remember that sometimes we had to integrate if we wanted to find this area of this parabola. Using a dx slice, no problem. Using a dy, we just go from 0 to the function, but using a dy slice, well, this parabola is not invertible. So using a delta y is not as convenient as using a delta x. The same thing can happen with double integrals. In some cases, a dx dy integral is going to be more convenient than a dy dx integral. So we have to know the procedure. We have to understand the procedure, not just be able to imitate. All right, that's it. That was a big idea today, especially for a Monday. Double integrals. What's x between? What's y between? We'll practice this more tomorrow. We're going to take this same kind of region, then we're going to start chopping it up in different ways so we can see what's x between, what's y between. Any questions? Comments? Deep thoughts? All right, that's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day. Thanks for playing.